In the name of God, the most gracious, the most merciful, praise be to God, and may prayers and peace be upon the messenger of God, our Master Muhammad, and upon all his family and companions. And now, by the declining day, indeed mankind is in loss, except for those who have believed and done righteous deeds, and advised each other to truth, and advised each other to patience. The summary of what has been mentioned is that we have three methods to ensure that the relay coordination is correct. Either using time, or using overcurrent, or using both time and overcurrent together. The common goal of all three methods is to achieve correct discrimination, meaning the proper identification of the fault. Here, discrimination refers to isolating only the part where the fault occurred, leaving the rest of the electrical system that did not have a fault without any problems, meaning isolating the fault and leaving the rest of the network stable. Time discrimination leads to long tripping times. Closer faults need shorter tripping times. Short parallel lines need significant impedance to locate faults. The tripping time becomes long near the power source due to the time coordination between different relay devices and the drawbacks that arise from the fact that a large fault requires a long time to clear. On the other hand, there are challenges arising from the difficulty of time coordination when there are two short and parallel lines, which can only be applied if there is a significant impedance value between the circuit breakers. To identify the fault location, a third method combines previous methods, maintaining an inverse relationship between fault current and tripping time. It is unaffected by transient faults and trips quickly during high current faults, known as the inverse time over current relay characteristic. This method combines the features of the previous two types, maintaining an inverse relationship between the fault current and the tripping time. It is characterized by not being affected by transient faults, which is one of its advantages. At the same time, it trips quickly during high current faults. What is the inverse overcurrent relay? They are usually provided with a set of curves to suit all uses and to give different speeds, and different separation time speeds for the same current value, and the degree of slope of each of these curves differs from the other. There are several types, including the standard inverse characteristic, the very inverse characteristic, the extremely inverse characteristic, and many other curves. Each type of these curves has its specific uses and is said to be part of a certain operation. The moving regulators use a system of skills for the moving regulators and the skills of the moving regulators. The second change is to shift from a major change to a minor change.
The moving organizations use the moving organization skill system and the moving organization skills. The second change is to shift from a major change to a minor change. This change is called the second change. If this change gains a value of change in a short time, then the change will introduce a mechanism to modify the change. This change is called the second change. If this change gains a value of change in a short time, then the change will introduce a mechanism to modify the change. The cooperation between the change and the second change drives the value of the change. The relationship between the pickup current and delay time is defined by the tripping characteristic curve. Essentially, the relay will trip increasingly faster as the overcurrent increases. It is prescribed that the relay will trip increasingly faster as the overcurrent increases, indicating that the relay will trip more quickly with higher overcurrent. There are different types of inverse time curves, such as long time inverse, normal inverse, very inverse, and extremely inverse. Adds individuality to comparisons that break its value. Comparing 10 or 100 is the same. Operates quickly after the value is broken. In the individuality comparison, this means that the individuality comparison is the same when comparing 10 comparisons and when comparing 100 comparisons. The individuality comparison is when the individuality operates quickly after the individuality value is broken. This means, and the meter is distinguished in a way. Almost. And how to achieve the area. The exchanged area is also achieved with things that follow in many other stations.
Before explaining these curves, know there are two global standards that describe these characteristic curves. The first standard is used in North America, known as the ANSI or IEE standard, and the other is the European IEC standard. Each curve has its own specific equations, so ANSI and IEC very inverse curve equations differ. This is a common mistake. If setting the overcurrent relay to very inverse, know which standard it belongs to, American or European. Be aware of this for both standards. Typically, IEC is used in most companies, while ANSI is used in some American companies. The IEC 60255 uses 5 curves: standard inverse, very inverse, extremely inverse, long time inverse, and short time inverse, while ANSI uses 4 curves. You should know this, whether you follow American or European, or even other international standards. The IEC standard is used while the ANSI curve is used. IEC 60255 uses 5 curves: standard, very, extremely, long, short. ANSI uses 4: standard, power, extremely, long, short. X-axis shows fault current ratio to setting current, called percent of pickup. Previously, it was BSM plug setting in electromechanical relays. These are the standard, power, extremely, long time, short time inverse. ANSI uses normally, very extremely, moderately inverse. The X-axis shows the fault to setting. These are the inverse curves. Note the X-axis does not show the current value in amperes. It shows the ratio of multiples of the fault current. This is the percent of pickup, expressed as I major relative to I pickup or I fault relative to I setting. Now let's explain one curve and compare them. SM plug sit-in multiplayer. It is expressed as the value of I major relative to I pickup or I fault, relative to I setting. Now let's take one curve to explain all the details, and then we will make a comparison between the different curves. For example, the IEC standard inverse trip time equation is T or TMS 0.14, IR 0.02, 1. Here, IR is the percent of pickup, which is the I fault relative to the I setting or I major relative to I pickup, known as PSM in electromechanical relays. TMS is the time multiplier setting. The trip time is influenced by TMS and the fault current multiples relative to the setting current. Increasing the fault current reduces the trip time as it is in the denominator. Electromechanical relay, while TMS is time multiple setting. As is evident from the equation, the trip time is controlled by 2 factors, TMS and the multiples of the fault current relative to the setting current. We can see from the equation that increasing the fault current will reduce the trip time because it is placed in the denominator. As for TMS, which stands for time multiplier setting, it is a factor that controls the trip time value. If the TMS value is greater than 1, the trip time will increase, and if the TMS value is less than 1, the trip time will decrease. It's important to note that the term TMS is only used in the European standard, while the American standard uses the term TD, and both mean the same thing. Notice with me that if we set the IEC normal inverse curve or standard inverse curve with a fixed TMS value and then change the pickup value, the curve will shift to the right. If we fix the pickup value on the normal inverse curve and change the TMS value, you'll see that the curve moves up or down, and both mean the same thing. Notice with me that if we set the IEC normal inverse curve or standard inverse curve with a fixed TMS value and then change the pickup value, the curve will shift to the right. If we fix the pickup value on the normal inverse curve and change the TMS value, you'll see that the curve moves up or down. For example, if my setting current value is 3 amperes and the curve used is normal inverse with a TMS value of 1, and the fault current is 6 amperes, when will the relay trip? The trip time will be calculated by applying these parameters in the normal inverse or standard inverse equation, which is T equal to 1, which is TMS multiplied by 0.14 over, which is, on me, 6 over 3 means 6 is the value of the fault current over 3, which is the setting value, all raised to the power of minus 1. The resulting time can be found without any equations using the normally inverse curve. So we go to the x-axis and look for the number 2, which is 6 over 3. We said that the out x-axis represents the percent of pickup, which is 6 over 3. At 2, we draw a line and it intersects with the line at 10.03 seconds. On 10.03 second. So when setting the final setting for the inverse overcurrent relay, we need 3 essential pieces of information. The first piece of information is the type of curve used, whether it's an IEC curve or an ANSI curve, along with the TMS value and the backup setting value. Now let's compare the different IEC inverse curves with each other, considering that their TMS value is 1 and the I setting value is 0.1A. Relay inactive. 0.1A. When the measured current value is less than 0.1 amperes, the relay will not give any indication while the measured current is below the setting value. If the current exceeds 0.1 amperes, the relay sends a warning signal indicating a trip. When the measured current reaches 0.2 amperes, e.g., the 0.2 here means it is double the setting current, which is 0.1, thus 0.2 divided by 0.1 equals 2. The relay will trip after a time of 10.02 seconds using normal inverse, after 13.5 seconds using very inverse, after 26.6 seconds using extremely inverse, and after 120 seconds using long time inverse. 0.2 divided by 0.1 equals 2. So the relay trips after 10.02 seconds with normal inverse, 13.5 seconds with very inverse, 26.6 seconds with extremely inverse, and 120 seconds with long time inverse. As current increases, trip time decreases due to the inverse relationship. Compare normal inverse and extremely inverse curves. Normal inverse is used in ANSI or IEE curve, not standard inverse, a common mistake. Note that the higher the value of the current and the fault, the shorter the separation time as well, because as we said, the relationship between current and time is an inverse relationship. Now let us compare between normal inverse and extremely inverse curve. Note that we say normal inverse and not standard inverse, and this is a common mistake among engineers, as the curve is described as normal inverse only in the case of the ANSI curve, characteristic, or IEE curve. Just in case, or it is described as IEC standard inverse. Extremely inverse trips slower than normal inverse at double setting. Normal inverse trips in 10s, extremely in 26. At 10x setting, normal trips in 2.9s, extremely in 0.8. Comparing extremely inverse and normal inverse, trip time is longer at double the setting. Normal inverse trips after 10 seconds. Extremely inverse after 26 seconds, a long time. At 10 times setting, normal inverse trips in 2.9 seconds, extremely inverse in 0.8 seconds. Prefer extremely inverse for high inrush current at startup as it should not trip. Extremely inverse is ideal for high inrush currents at startup, preventing false trips. It suits motor loads and low voltage distribution with transient faults. Very inverse, between extremely and normally inverse, is best for high fault impedance due to distance. It has a steeper slope than normally inverse. We know that the value of the starting current will naturally exceed the I setting value, so it is preferable to use the extremely inverse curve to reduce the number of false trips during the starting current, especially if the load consists of motors. It is also advisable to use the extremely inverse curve with the outer closer used in low voltage distribution, as most faults that occur on it are transient voltages under normal conditions. Very inverse is an intermediate case between extremely inverse and normally inverse or standard inverse, and it is preferable to use it when there is a significant drop in the fault current value due to increased distance from the power source, meaning when the fault impedance is high. When comparing very inverse to normally inverse or standard inverse, we will notice that very inverse is more steeply sloped or more inverted than normally inverse. When we say steeper or more inverted, it trips faster than the normal inverse for the same fault. For example, trip time at 10 times the I setting value for extremely inverse, 0.8 seconds, for very inverse, 1.5 seconds, and for normal standard inverse, 2.97 seconds. Greater slope inversion means less trip time. Standard normal inverse is typical for most network voltage levels, used as backup in high voltage, main in medium voltage. Combine IDMT with instantaneous overcurrent for a curve starting inverse, ending instantaneous. So the greater the inversion or slope, the shorter the trip time. Inverse is used in voltage levels as backup in high voltage and main in medium voltage. IDMT curve combines with overcurrent curve, reducing tripping time. Custom curves can be designed for specific factory needs. IM protection and can work between the two and any work between them so that the begins and ends, and it reduces the tripping time in cases of high fault levels. It's also worth mentioning that you can design your own custom curves to fit different or specific cases in the factory you work in. This feature is available in various IED releases, but it is rarely used. the Renaissance, more of a nation,